Hi, good evening. In this video, we are going to be discussing section 5.5 on the properties of logarithms. So we'll be using properties of logarithms to expand and condense logarithms. We'll also be using them to simplify, to evaluate. And then a little bit later, so in our next section, we'll start using the properties of logarithms to help us solve equations. So here are the properties. The first one is called the product property for logarithms. And that says that log base a of m times n is equal to log base a of m plus log base a of n. So it doesn't matter what the base is, doesn't matter what m and n are. They could be variables, they could be numbers, they could be expressions. But if I'm multiplying inside the argument of one logarithm, I can expand it to multiple logarithms with addition. Kind of the opposite of that is the quotient property. So log base a of m divided by n is going to equal log base a of m minus log base a of n. Where again, it doesn't matter what the base is, doesn't matter what m and n are. If I'm dividing inside the logarithm, I expand that with subtraction. And all of these properties can go both ways. So if I have addition between two logarithms, I can make that into one logarithm using multiplication. So we're going to be going both ways today in class. Our next property is the power property. It says if I have log base a of m to the power of r, I can rewrite this as multiplication. So I can write this as r times log base a of m. This is a really important property when we get into solving exponential equations with logarithms. So we take the logarithm of our exponent, which allows us to then bring the exponent down and solve this more like a linear equation instead. And then the last property we're going to talk about today is when the base matches the argument. So log base b of b is always equal to 1. And that's because remember that our logarithms are asking what power can I raise the base to so that it's equal to the argument. So if the base and the argument are the same, b to the power of 1 equals itself. So this goes for any base. Remember, our kind of two most important bases were the common log, where I don't actually write out, but the base is 10. So the common log of 10 is 1. And then the natural log, where the base is e. So the natural log of e is equal to 1. Right? But this works for any base. So log base 2 of 2 would equal 1. Log base 100 of 100 would equal 1, as long as the base matches the argument. Okay, so make sure you have these properties written down because we're going to keep coming back to them throughout class today. We're going to start with using these examples to help us evaluate logarithms. Always keeping in mind what a logarithm is asking us, right? What power can I raise the base to equal the argument? So for this first example, I have log base 2 of 2 to the power of negative 13. So I immediately see that the base matches the argument, but I also have this exponent. So before I can simplify, I want to get rid of the exponent, and I can do that using the power property that says I can bring this down as multiplication. So this is negative 13 times log base 2 of 2. Now we already said before that when the base of a logarithm matches what's inside the logarithm, that is equal to 1. So this is negative 13 times 1, which is just negative 13. So we use our properties and we simplify the logarithm. Okay, next we're going to use our properties again. We have log base 6 of 9 plus log base 6 of 4. I'm asking, what can I raise 6 to a power of to get 9, or what can I raise 6 to a power of to get 4? And that is technically possible, but it's not going to be a whole number. It's not going to be an integer, right? Because 6 squared is already 36. That's too big. So before I can evaluate, I'm going to try simplifying by bringing these two together using the product property. Remember, addition on the outside is equal to multiplication inside our logarithm. So we can do log base 6 of 9 times 4. 9 times 4 is 36. And then from here, I can evaluate either just by kind of knowing what the logarithm is asking, or the way we did this in class last week to evaluate is we set the logarithm equal to x, and we rewrote this as an exponential equation where we have our base to the power of x equals 36. 36 is 6 squared. So if 6 to the x equals 6 squared, x equals 2. So our original expression reduces all the way down to 2. Okay, let's do another one. This time we have log base 8 of 16 minus log base 8 of 2. So I'm going to start with bringing these together. I see subtraction between the two logarithms, so I'm going to use the quotient property. Subtraction on the outside comes together with division. So 16 divided by 2. 16 divided by 2 is 8. So I have log base 8 of 8. The base matches the argument. Base is the same as what's inside. So by our definition, we know that equals 1. Right, this next one has 3 logarithms. That's okay, we can still use our same properties. So we're going to combine these again into one logarithm and then evaluate. So we're going to do it kind of one step at a time. We'll start with our first 2 logarithms and we'll move from the left to the right. We have log base 2 of 20 minus log base 2 of 10. Remember again, subtraction outside goes to division inside. So this is log base 2 of 20 divided by 10. And then I still have this plus log base 2 of 64. Twenty divided by 10 is 2, so this is log base 2 of 2 plus log base 2 of 64. Now from here, I could actually already evaluate, because I know, again, log base 2 of 2 is 1, because the base matches the argument. I also know that 64 is a power of 2. Count it off. I can do 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32, times 2 again is 64. So 64 is 2 to the 6th power. So I could say this is 1 plus 6, which would be 7. But I'm going to keep going and condense it all the way and then evaluate. So we're going to do log base 2 of 2 plus log base 2 of 64 comes together using our product rule. This is 2 times 64. 2 times 64 is 128. 128 is 2 to the 7th power. So log base 2 of 128 is 7. Which is the same thing we would have gotten if we had converted this to 1 and 6. 1 plus 6 is also 7. Okay. So now we're going to start looking at, instead of actually being able to evaluate logarithms, we're going to be putting variables in. And the first direction we're going to go is expanding, and then we're going to do the same thing by condensing. So we're going to write each expression as the sum or difference of logarithms. And we're always going to express powers as factors when we do our expansion. So that means if I have an exponent, I always want to make sure I bring it down as multiplication using that power rule. So our first example for this is log base 3 of x divided by 9. So we're going kind of the opposite direction this time. I have division inside the logarithm. So I'm going to expand this to log base 3 of x minus log base 3 of 9. In this case, 9 is 3 squared, so I could also rewrite log base 3 of 9 as just 2. So this would be log base 3 of x minus 2. That would be fully expanded and simplified as much as possible. Right, next I have the natural log of x times e. Just remember from last class, a quick little review. The natural log is equal to log base e. That doesn't really matter here. We treat the natural log just like we would any other logarithm, has the same properties. So multiplication inside is going to go to addition outside. This is the natural log of x plus the natural log of e. Natural log of e is that special property where the base matches the argument. Remember, again, this is the same thing as log base e of e. So this is equal to the natural log of x plus 1. Okay, next we're going to combine a couple properties. I have log base a of u cubed times b squared. So we're going to expand, and then we're also going to use our power property to make sure we always express our powers as factors, not fractions. Okay, so first of all, these are being multiplied. So we're going to expand this with addition. This is log base a of u cubed plus log base a of v squared. Great, so we did our expansion, but we're not quite done. We also want to bring our powers down using the power property. Do that for both of these logarithms. So it'd be 3 times log base a of u plus 2 times log base a of v. And that would be our full expansion. Okay, we have another one. And this one is a lot, right? We have a lot going on. We have x cubed times square root of x plus 1 divided by x minus 5 squared. So we have kind of three expressions that we're working with. Our three expressions here are x cubed, that's being multiplied by square root of x plus 1. And then both of these are being divided by x minus 5 squared. So we have three separate expressions, which means we're going to expand this into three logarithms. So to start, let's get rid of the division since everything's being divided. We get rid of division with subtraction. So this would be log of x cubed times the square root of x plus 1 minus log of x minus 5 squared. Now, inside this first logarithm, I still have multiplication. So this is x cubed times square root of x plus 1. So I separate those with addition. So we have log of x cubed plus log of the square root of x plus 1 minus log of x minus 5 squared. So now I'm almost done. My last step is, again, to get rid of these exponents. Remembering that the square root is technically an exponent. Square root of x plus 1, remember, is the same thing as x plus 1 to the 1/2 power. So when we write this in radical form, that's just another way of saying the power is 1/2. So for my last step, I'm going to bring the exponents down, and that includes this power of 1/2. So I get rid of the square root by bringing the power down. So my last step is to write this as 3 log x plus 1/2 log of x plus 1 minus 2 log of x minus 5. So it's fully expanded with all of my exponents written as factors or as multiplication. All right, this one is pretty similar. Instead of having multiplication in the numerator, we just have multiplication in the denominator. Another thing we might notice about this one is where our last example, there was nothing I could simplify before I got started. There are no common factors in the numerator and denominator. But in this example, we do have common factors. I have an x cubed and an x squared. So I can divide the x squared completely out and take away 2 powers from x cubed. So this is just now x. So I simplify those common factors first, just like we did when we talked about rational functions. So that this is now the natural log of 4x over 7 times x plus 2. So that got rid of all my exponents. I don't have to worry about, at the end, writing my exponents as factors. This time I have quite a few expressions. This is 4 times x divided 7 times x plus 2. So let's again get rid of the division first. We're going to expand that to subtraction. So we have the natural log of 4x minus the natural log of 7 times x plus 2. This is 4 times x. I can expand that multiplication with addition. So the natural log of 4 plus the natural log of x minus, this is the natural log of 7 times x plus 2. And we have to be really careful here because we're going to expand this, but our entire expansion is still being subtracted. We're going to put that in parentheses. We expand this with addition, natural log of 7 plus natural log of x plus 2. And this is where students usually make mistakes because the subtraction goes to everything in parentheses. We expanded it with addition, but we have to remember to distribute that minus sign. So this really becomes the natural log of 4 plus the natural log of x minus the natural log of 7 minus the natural log of x plus 2. So both of these are negative because they both started in the denominator. Okay, so that one was pretty tricky. Now we're going to go the opposite direction. We're going to express these as single logarithms. Excuse me. So for this first one, I have the log base 3 of x squared plus 3x plus 2 minus 2 times log base 3 of x plus 1. I want to bring these together. I have subtraction between, so I know I'm going to use the quotient rule. But before I can do that, I have this 2 on the outside. I need to get rid of that by bringing it back up as an exponent. So we use the power property first. I can't bring these together if it's being multiplied by something. So this becomes log base 3 of x squared plus 3x plus 2 minus log base 3 of x plus 1 squared. Now I can bring these together with subtraction. Subtraction on the outside goes to division on the inside. Now this is technically fully condensed, right? We expressed it as a single logarithm, but we can actually reduce here the expression inside our parentheses. So this is a good little review of what we did with rational functions in chapter 4. Remember, to reduce a rational expression, we want to write everything in factored form first. So here, to write our numerator in factored form, we're looking for two numbers that multiply to 2 and add to 3. That would be 2 and 1. So I can write this as x plus 2 times x plus 1 over x plus 1 squared. So these have a common factor of x plus 1 in the numerator and denominator. The one in the denominator is squared, so I can get rid of one of them. And then I can write my final simplified answer as log base 3 of x plus 2 divided by x plus 1. So we expressed it as a single logarithm and we simplified completely. Okay, another example of condensing. This time we're condensing 3 logarithms into 1. Before I can start to condense, remember I always want to get rid of those factors on the outside by bringing them up as exponents. So here this was 5 times log base 2 of v. I want to rewrite the 5 as an exponent. So we have log base 2 of u plus log base 2 of v to the 5th minus log base 2 of u to the 4th. So we'll condense 2 at a time. Log base 2 of u plus log base 2 of v to the 5th will come together with multiplication. And then that's still minus log base 2 of u to the 4th. Subtraction comes together with division. So I've condensed it to a single logarithm, but again, I can still reduce here. I have a u and a u to the 4th. So I can reduce one factor of that. The u in the numerator just cancels, and I reduce down to u cubed in the denominator. That would be my final simplified logarithm. Okay, so we did expanding and condensing. Next, we're going to talk about the change of base formula. The change of base formula comes into effect mostly because when we're dealing with just like a regular kind of desk calculator, we can't change the base of the logarithm. So we're usually going to be given either just the common log or the natural log. So if we're given a log with a base of something different, we can use the change of base formula to help us evaluate on our calculator. So the change of base formula says log base a of x equals log base b of x divided by log base b of e of a. So we can change the base to whatever we want, and it's the log of what's inside divided by the log of the original base. We're going to always change the base to either e or 10 for common log or natural log. So for example, log base 5 of 18. I'm going to change the base using the common log. I can write this as log of 18 divided by log of 5. This I can evaluate in a calculator. I have the common log right on the home screen, so I would do log of 18. Don't forget to close your parentheses. Divided by log of 5. It's 1.7958. We're going to round to 3 decimal places. So we'll round to 1.796. Okay, let's do log base pi of e. So it's kind of a weird expression. This time, since I see I have it working with e, I'm going to use the natural log instead. It doesn't matter, I could still use the common log, it would still give me the same answer. But since e is the base of the natural log, we're going to use that. So using the change of base formula, this would be ln of e divided by ln of pi. I already know the natural log of e is 1 by definition. So this is 1 over the natural log of pi. And I can evaluate that in my calculator again. 1 divided by, this time natural log is right below that common log. You also have a pi button on your calculator that is right above division. Oops, that's not what I meant to do. So we have to hit second and then that button to get the pi. We get 0.8735. Rounding to 2 decimal places would be 0.874. Again, we could have just typed it in originally if you didn't notice that the natural log of e switched to 1. Your calculator would have known that for you. You would have gotten the same answer either way. Okay, so that is our properties of logarithms. Again, we had our product, quotient, power, base matches the argument, and then lastly, the change of base formula. Make sure you do your homework for this section to get your practice in. The properties are kind of fun to work with, but they take a lot of practice to recognize and reduce. So make sure you get your practice in and let me know if you have any questions.